Good morning, my trailblazers. Good morning from Pennsylvania, 6 a.m. on Friday. If anybody is here, it means you are real digital pathology trailblazers. I'm going to drink my coffee and my Polish cup because this week we're going to Poland with the whole family. So next month, we're going to skip the live streams. Because I'm going to be working on something exciting in Poland. What I want to do is to revive the membership where all the digital pathology resources that we created live and design a better learning experience.
Learn about the newest digital pathology trends in science and industry. Meet the most interesting people in the niche and gain insights relevant to your own projects. Here is where pathology meets computer science. You are listening to the Digital Pathology Podcast with your host, Dr. Alexandra Zhurov.
So what happened is I stopped sending emails every live stream, and because it was a lot of emails, and we realized that when I posted on social media, also the same amount of people knows about the digital pathology live streams, about our journal clubs. So we stopped bombarding the email list, but then I started getting emails. Hey, put me back on the list. I don't know if you're doing the paper reviews or not. So I'm going to be redesigning that a little bit. And next month, while in Poland, I'm going to focus on finally finishing the book, Digital Pathology 101, All You Need to Know to Start and Continue Your Digital Pathology Journey, which you can get from the digitalpathologyplace.com book for free as PDF. So if you don't have the book yet, go get the book. And today we're gonna review a paper and a topic about pathology foundation models. So the original paper cover is this one. And yeah, what about these foundation models? What about the foundation models? Like, so much hype. Where are they? And I'm going to tell you where they are based on the paper and based on some information that I have from other digital pathology trailblazers on the vendor side. But we're going to be discussing pathology foundation models, evolution, current landscape, challenges and opportunities, and clinical perspective. Opportunities from a technical and clinical perspective. That's what we're talking about today. Let's see. What about these foundation models, right? What about them? Where are they? What's happening? Like, how difficult is it to use them? Where, like, I love them, or I could potentially love them, but where are they? How can I use them? Some are open source, some are not. So that's what we're going to be talking about the evolution and current landscape. Obviously, there are challenges and opportunities. So let's get into it. Why did they even start existing? Well, first of all, I bet it was fun for computational pathologists, for computational pathology scientists to start using the newest methodology, and we're going to talk about it. But from the global perspective, the rising volumes of anatomic pathology cases, right? Contemporary anatomic pathology faces increasing case volumes. And then not only this, ancillary studies, routine specimens now require other types of testing, like molecular assays and obviously immunohistochemistry. So it's not just H&E. We know that. Cognitive load. Because of these ancillary studies, the pathologist is now not only looking at slide, recognizing a pattern and saying this or that, or which is also different from what it was when they trained, because the WHO changed the criteria. That's another topic. But basically, the cognitive load is pretty high because multimodal data integration increases turnaround time and interpretative burden for pathologists. It's difficult, including like all the other ancillary studies. So there is a need to shift from purely morphologic assessment to systematic, high variable complex data. And the leverage can be pushed by scalable AI and pathology foundation models. So what happened, like what was the evolution? The evolution was, in the past, we had very task-specific models, and now we are supposed to have task agnostic, meaning it's going to do it all. Like a pathologist, it's supposed to be brilliant. So before we had the early models when convolutional neural networks entered the scene, I was ecstatic because I didn't have to like deliberate with my image analysis colleagues what is the threshold and where do we put the threshold, because if we put it too high, for example, DIB staining in IHC, then we lose faint cells. If we put it too low, then we get false positive cells. Where do we put it? And you couldn't put it all the time in the same place. And then CNNs appeared, and that was a miracle. But CNNs would give you a single task output. So that's a little bit limiting, because then for every single pathology task, the narrow AI is going to just do this one task. So there needed to be something better. Well, there wasn't the technology to have something better, but once the technology, also known as transformers, appeared, and by we I mean the broad digital pathology and computational pathology community, and specifically the computational arm of this community, they started working with transformers. So, and transformers are based on self-attention mechanism. So they like learn from the image what's happening in the image. So they can perform segmentation, classification. They can even tell you about prognosis. They can extract features, predict outcomes, and work on biomarker discovery. And every now and then you're going to have a paper that, oh, there was this data set. We already had it analyzed, but didn't tell the AI, and the AI figured out what the results were and like discovered. You know, we know the word validation, qualification and validation too well in the digital pathology space, but I'm always excited about this potential, right? So the self-attention mechanisms, they capture a long range of contextual dependencies without handcrafted features. And now we can input the huge whole slide image repositories. So that led to a breakthrough. The pathology foundation models, they learned to generalize, and they then would learn these generalizable representations that are reusable from massive whole slide imaging repositories. And I don't know how these people get the amount of slides necessary to train them, but they do get them. The main repository that is accessible for everyone is still the Cancer Genome Atlas, the TCGA, which has its own challenges, but it has just like, I don't know, tens of thousands. At some point I knew the exact number, but the numbers necessary for these models are bigger, a lot bigger. But okay, so how do you encode the whole slide image? Because the transformers, they came from text, and you don't have text, and you encode the text in tokens, which are not words, but like little pieces of text that contain some meaning, right? So what are our tokens? What are our tokens? Pathology tokens? They are going to be patches. And patches is nothing new in digital pathology, because patches and patching and like dividing these huge images into smaller pieces was necessary for any image analysis task. So actually, like the patches tokens for text, that was a new concept. But we had patches. So these are our tokens now. And then we have the transformer encoder. It's called multi-head. Well, it is described as multi-head self-attention models that can, like, they are multi-contextual. They can log-range contextual relationships between patches. So the key information here is that they can do this between patches. So like before, I think they still use the computer vision, all the computer vision capabilities like edge detection and all that stuff. But now they're even better, right? And then we have something called shared embedding. So this produces a compact feature vector representing the entire image. So basically we're encoding the patches into a vector of numbers. And what can we do with it? A lot. And this is amazing that we can do so much. We can do classification. We can do tumor subtype. We can do grading. So the classical computer vision tasks that you do, and they're described in the book as well. So grab the book if you don't have it, digitalpathologyplace.com. You're going to find it there right now. Then regression. So the regression, we're going to have the survival prediction, biomarker scores, segmentation, tumor regions. So what are we doing here? Dividing tumor from stroma, super important. Segmentation, tumor regions, tumor from stroma, so the tumor epithelium from stroma, and then finding nuclei there. That's going to be useful for immuno-oncology applications. And we can also do multimodal retrieval. So something I heard about in 2019 from a Google representative at Path Vision. So 2019, 7 years ago, right? I heard about Smiley, similar image retrieval, whatever, right? There is a multitude of these abbreviations that are invented for every paper to sound funny. And Smiley was something I was hopeful about. I'm like, oh, put it on the web. And I don't know where they put it, somewhere on GitHub or somewhere where the computational arm of computational pathology has access to. But basically this was image retrieval, where you could like paste an image and then retrieve similar cases, which is like a mainstream thing for consumer AI, where you can like crop an image. Go on Pinterest. I go on Pinterest, like there's a cool piece of clothing, like a nice dress, and I crop it and it shows me a bunch of other dresses like this. So this multimodal retrieval is for searching similar cases, and they can also be linked to genomics and clinical text. So a bunch of different types of data. And just not to overwhelm you, there's not so many types of data. There's image, there's text, there's probably voice that gets translated to text, a video, and tables. So that's that. And video is image as well, a version of image. But it's multimodal. The more, if it's more than one, it's already multimodal because you have two modalities. Let's look at the timeline to gigapixel scale, which is where we are right now. The transformer situation started with, in 2017, there was this paper, Attention is all you need. I think it was by Google as well. And they described this self-attention mechanism. And then in 2020, 2021, vision transformers and data efficient image transformers, they enabled the scalability to whole slide images. And 2022, we had something called masked autoencoder that allows for self-supervised pre-training. And here we are, more or less, we're already 1 year past 2025, and we had the emergence of gigapixel-scale foundation models trained on millions of whole slide images. I think I had some videos or information on this when this first came out, because I'm super excited by these new developments. Leading models by the numbers, we have vision-only models. Virchow 2, I think they came out from the Dr. Fox lab. Don't quote me on that, I think so. And then we have Mayo Clinic Atlas. You can quote me that this one came out from Mayo Clinic by the name. And then we have Uni. And the important thing is how many images were they trained on. So over 1 million for Virchow, 1.2 million for Mayo Atlas. And then Uni was on tiles. So this is whole slide images. The 1 million for Virchow and 1 million, over 1 million, 1.2 for Mayo Clinic, whole slide images, not patches. So because like the trick when you read these papers is like so and so many images were used, and by image they mean a patch. So you can create a bunch of patches from one whole slide image. So they always say, oh, so many patches, and like 20 whole slide images. I'm like, really? But here actually 1 million of whole slide images. I don't know where they come from the hospitals. Then, so these were vision only. Then multimodal, vision and language. We have CONCH, and this is over 1 million whole slide images. And it is, this CONCH is with paired text, superior for complex biomarker like microsatellite instability. So we have the report, you have genomics that says that this particular slide has microsatellite instability. So we are entering the space of molecular predictions from H&E, which is also something I'm super excited about, and I want to see it being deployed. And I'm super excited about any like case report or mention of this modality actually getting closer to clinic. And then we have other ones that they're called so-called hierarchical, where they work for their different tasks at different levels of the image. And here we have H-Optimus and GigaPath. So these are the main players. There's more, and probably as we speak, they're developing even more. So have you used any of them? Do you have like access to any of them? Let me know in the chat. So how do we evaluate clinical readiness of these? Well, the golden rule would be the pre-training data diversity. So what do we mean by that? We want to have, I'm just checking if I'm not frozen. Yesterday I was streaming about histology and I was frozen. So the golden rule, pre-training data diversity. The problem is, one of the problems is that the data used previously for training AI was not that diverse. So in the paper, they cite that the TCGA, 80% of this data set is from patients of European descent. So no data on Asian, Black, Indigenous, or any other population. It was mostly European. So here the golden rule is to have pre-training data diversity, different anatomical sites, cancer types. This outweighs the sheer data volume for downstream success. Here the top performers, Virchow 2, CONCH, H-Optimus 1 consistently lead across 60 plus clinical tasks on standardized benchmarks. And we have two benchmarks mentioned in the paper. There are more, PathBench and PathoBench. The PathoBench is specific for foundational models. And what is cool about these models, because they're like huge, big, billions of parameters, which I don't even know, like, I come from the classical handcrafted feature computer vision tasks, like how dark should the nucleus be to classify it as positive. So I'm like, I was trained on sliding one parameter at a time. These have billions of parameters, so beyond my comprehension. But so like adapting every one of these is a no-go. This is not happening, but there is an option to efficiently adapt them. they call it parameter efficient fine tuning, and one of these frameworks is called LoRa, and this adapts like one layer of these models, massive models, to specific tasks with minimal computational cost. So they're like pre-trained on what is an image, pixels, like all this general computer vision knowledge, edge detection, feature extraction, whatever, right? For the list, you go back to the paper. But basically, they already like have the knowledge how to interpret image, and then you train the top layer. That's how they refer to it, to train it for a specific task and make it a lot more efficient. But where do they struggle? We have they are not perfect, nor are the pathologists. But I'm a pathologist, so I like to believe we're more perfect than the foundation models. But if we can join forces, we're going to be even better. So, where do they struggle? The two usual suspects, cytopathology and hematopathology. Why cytopathology? The Z-stacking. Cytopathology, where for some areas of cytopathology, like pap smears, or maybe even like simple tasks for blood smears, but that would be hematopathology. But everything that you can make flat and nice and unified, also urinary bladder cytology, where you can do the thin prep, cytospin and thin prep, they look nice, and they have been models designed for that. But any other thing from cytopathology, where you like squirt a fine needle aspirates on the glass slide, stain it, and then you have different levels of tissue, that's going to be challenging because the models are trained on flat anatomic pathology images. And then hematopathology has a different problem because it relies heavily on multimodal ancillary studies, and these are flow cytometry and cytogenetics. So if a model was not trained with this data, you cannot deploy it on the hematopathology. Basically, well, the main thing is these specialties or these slides look different than the training data, than the million whole slide image models were trained on. So you just didn't train on this. If we had a model trained on millions of cytopathology images, maybe we could be better there, and the same for hematopathology. So the gap is that AI development has largely focused on common tumors, leaving rare disease and complex preparations underrepresented. Why? Because there's less data. You go where the data is to develop these methods, and you check, is your method good enough for the data that you have, and then you try to deploy it or like train it or get more data for the places where it's underperforming. There may be enough data, there may not be enough data, but then like you will have underperformance on the missing data. What else is problematic? Something artifacts and concept drift. So domain shifts and shortcut learning. Do you see this pen here? I heard about this pen in 2019 the first time, and I was like, really? Yes, really. So models fail due to fixation variations. So the domain shift is like that the slides look different from different places, from batch to batch. We also have scanner artifacts, and the models are exploiting non-biological features. Pen marks, my friends, pen marks, my trailblazers. Where do these come from? Where a pathologist marks something under the microscope, because how else are you going to find it or show it to somebody else if you don't have a pen mark on the slide? And I used to do this too when I was not working on digital slides. Now I have digital pins, which I love. Really, like, thank goodness for digital pathology. It's game changer for my life. I love it. You know that I love it because I talk about it all the time. So yeah, but it's not perfect, nor are we. There's also something called concept drift. I briefly mentioned it, evolving diagnostic criteria, evolving clinical criteria. So the guideline updates, the WHO guideline updates, they cause performance drops over time, not because the performance changes, but because now the labels or the reports or the information used to train the models is no longer the same information that we are applying to. So like if there is a specific diagnostic term that changed, now the label changes. So the performance drops because the model doesn't deliver the new label anymore. Anyway, so there is a solution. They propose a solution, a multi-site validation and explainable AI. And there are different concepts to have different like ways to have AI explainable. What they talk about is something called counterfactual explanations are required to diagnose black box failures. And I liked this way of explaining, maybe because I didn't know it before. I knew the attention maps where the model shows where they took the information from, but this one is even better because it shows you the places where if the evaluation would change, and whatever the evaluation is, like scoring or some kind of like parameter calculation would change by a certain percentage, the diagnosis, the label, or the task would be performed differently. So let's just take a nucleus detection something. So to explain, okay, why am I detecting nuclei? Because if something would change in this area of the nucleus by so and so many percent, I would not classify it as a nucleus, and therefore this is where I take this information from. One of the ways to check it, and there is a whole branch of science called explainable AI, which they abbreviate XAI, XI or XI. Explainable AI, big thing in clinical space, in medicine, because the black box problem is bothering medical community very much. So we're trying to explain the black box always when we can. But we also have, I call them so-called life hurdles. So now you have this amazing model. It lives somewhere in our imagination or in the internet cloud or wherever it lives. I cannot take it and deploy it on my whole slide images that I have in my collection. And if I'm operating in a regulatory environment, don't even touch it. So there are life hurdles. And one of these hurdles is regulatory. Although I think in this particular case, they throw the FDA frameworks under the bus a little bit too much. So the authors of this paper say that FDA frameworks struggle to classify continuously learning or task agnostic systems. So continuously learning, I have a problem with this, because when you submit something to the FDA, this version of the thing is not continuously learning. You can then train it and have a different version. And FDA has frameworks for that now, and that are, what do they call it, like predetermined change control. If you know the exact name, let me know in the chat. But they are like, let me tell you where all these frameworks and regulatory inputs are easy to find. There was this 7-part AI in pathology series by Rashidi et al. And we had a full series of DigiPath Digest on every single paper. And there was this paper about a regulatory aspect of all these AI evolutions in pathology. And the amount of frameworks from different regulatory bodies is huge. So once I saw the table, like, okay, in Europe, in this country, framework for this, for that, for risk, for fast approval, for this, that, whatever, I'm like, FDA has some smart people, fast thinking and fast adapting people on their team. And obviously, FDA is huge, and other regulatory agencies as well, because that's their goal, to provide to maintain the safety of these tools. So I would say it is a hurdle. Regulatory always is a hurdle because you have to put a lot of effort into regulate these things, which is good. And FDA is evolving, although probably slower than the science, but that is how it's supposed to be. Like you're not going to regulate every scientific discovery. It has to be good enough. It has to be qualified, and there has to be a path forward for this. So, it's a chain. Anyway, infrastructure. I probably would not be able to deploy this model or train a model that is based on gigapixel images, and this demands high performance GPUs and then LIS integration. And you can argue this is difficult, but you can do it, but cloud, whatever. It is a life obstacle that needs to be overcome in whichever way you want to overcome it. Infrastructure is infrastructure. Labs were not built with the newest infrastructure in place right now from the get-go, and they don't change things every week. So interoperability, infrastructure is a hurdle. Then workflows, disrupting time-sensitive pathology workflows. We want to have nothing of that. And I experience it firsthand every time I work with like a software upgrade and then it has some glitch. So that's tough because as much as I love digital pathology, I don't love to be slowed down. And then in many instances, and me, the digital pathology enthusiast that wrote the book Digital Pathology 101, is saying this. In many instances, if like it takes longer to open the image, if I had the glass slides, I would be putting it under the microscope and just reading it. But you do either or the other. Some, in the transition periods, you have both. Anyway, the workflow, if you slow down the pathologist, you're slowing down care. You don't want to do that. So important, right? And economics. Economics means you have to buy these things. So every time you have to buy something, you have to figure out where the money comes from. And there are ways to get it, but these are not the classical ways. So obviously lack of classical ways, and the authors cite reimbursement pathways, uncertain. I think they're being generous. Lack of reimbursement pathways, not for everything, right? So you need to be creative for the economics to work, or wrap it up into a larger, maybe enterprise deployment framework. Like you need to think how the economics are gonna work, and there is no guarantee that they're always gonna work, right? And the last concept is we are augmenting, not replacing. And that's actually for everyone, I think, not just for pathologists. So we're augmenting, not replacing, not just for pathologists, for lab personnel as well. As with any change, as with any disruptive technology, and I consider the foundation models a pretty disruptive technology, there's fear. Hey, well, my job is going to still be there in 5 years, 10 years, and some jobs will probably no, not jobs. Some tasks within a job will disappear, and I'm happy for them to disappear. Like, for example, as a pathologist, like if you make me count cells, I'm going to flat out refuse. If you make me guesstimate a biomarker, that's going to cost me a lot of energy. So if this task disappears for me, I'm all for it. For example, lab personnel, I think if the task of cleaning slides and loading them into the scanner disappears because a robot is going to do that, I think they're going to be happy because they can do then like more cognitive rewarding task than putting slides into the scan. Well, I don't know if people still do that, but at some point in the digital pathology evolution, that was the case, and not everything is automated. But anyway, the point I want to convey is the jobs will change, and you need to adapt. We need to adapt to change, and that's life. But we don't want to replace anybody, and the AI output serves as powerful decision support tool and not autonomous replacement. And when we say decision support tool, there is also caveats to that, because there is something called confirmation bias and different types of biases. So everything is multifaceted, but it's a positive change. Decision support tool, not autonomous replacement. Then pathologist refinement. We'll have interactive frameworks, retrieval-augmented and or conversational. This is fantastic option, I would say. So how I would use it, obviously I would just chat with it and talk to it. I have voice-to-text software on my computer for every possible app. So for my pathology workflow, I would do the same. And retrieval of images, that's so cool, because I remember, in one study, I saw this type of lesion. What did I call it? In toxicologic pathology, you have like a specific glossary. It's similar to clinical, but like there is a special list of terminologies, the international nomenclature of these preclinical terms. So you want to stay consistent, but there is always more terms for one lesion. So I would retrieve the image and check what I called it before. And so that would allow pathologists to query, refine, and validate outputs. And continuous learning, interpretability maps model outputs to recognizable histologic features, for example, nuclear atypia, to build trust over time. So interpretability is super important. If that would be something that a pathologist can verify, that would help tremendously, I think, with regulators and with the trust of the community in the validity of the tool. And that feeds directly, of course, into that this would be decision support. So it's a cycle that has to be deployed responsibly. And what about converging clinical data? It would be fantastic to have this comprehensive disease modeling to include histopathology, radiology. These two are image-based, right? So they're perfect for this. Then we have genomics and clinical notes. So here we have this multimodality, and to align with real-world diagnostic reasoning, models must integrate beyond just image. So the hope is in vision language, models that offer a promising pathway towards fusing clinical data. Vision language. Would we cover everything with vision language? Yes, this is language. Sorry. Language, vision, genomics. I'd say it's letters, so let's call it language. I don't know, it's different. But letters are used for the basis. So the authors propose a path forward. We had this shift. The models have moved computational pathology from narrow algorithms to scalable, reusable frameworks. So here, a point to consider: the narrow algorithms didn't disappear, and they're still useful. And all these new technologies exist in parallel, right? We have a challenge because bridging the gap between controlled experimental benchmarks and highly variable real-world clinical workflows is challenging. So it's like taking an experiment from a very clean, sterile lab into the real world. Your sterile control conditions disappear, and that's the same on the computational pathology side. And they also propose a solution that the field must prioritize deployment-centric design, prospective multi-institutional trials, and human AI interactions. deployment-centric design. This is good. Prospective multi-institutional trials and human AI interactions. For this to actually reach the clinic, I like to say that life is a funnel, right? You have to do a bunch of science at the basic level to see what sticks, what works, and then the stuff that works, okay, can you then think of deployment? It's like drug development, right? You have so many candidates and only like 1 or 5 make it to the bottom of the funnel and then are going to end up in patient treatment. You're not going to go and validate everything that's at the top of the funnel. It has to pass all the other steps to be at the bottom to actually do a clinical trial on this particular drug candidate. So here the same, instead of drug candidates, we have like model candidates, algorithm candidates, or whatever the computational equivalent is to this chemical compound that goes into a drug development pipeline. And then once it's far enough down the pipeline, let's do it. Let's prioritize deployment-centric design, multi-site trials, and the human AI interaction. So for this human AI interaction to be possible and to be useful, we need to know enough about AI. So that's why you guys are here. That's why we're doing the DigiPath Digest. And at the beginning, I said I'm going to be reinventing the membership that we used to have like a year ago, maybe 2 years ago. We have, I had a lot of resources there for you to study. I am reinventing this membership so the learning experience is better, so that you have a very clear path forward and to learn about AI, to increase your AI literacy in pathology. There's also going to be a separate path for histology and tissue recognition. So if you're interested in that, it's going to be in there. And nothing, like there is no launch date or anything, but I'm letting you know. So if you're interested in learning more or letting me know your preferences, let me know in the comments, send me an email, just get hold of me and say, hey, you said membership is coming back. I'd like to be part of the new version. So now I'm just gonna clap to everyone who was here till the end. You are the real digital pathology trailblazers. You are the reason I keep going, and every time you listen to this information and carry it forward, you are advancing digital pathology. So thank you so much for being here, and I'll talk to you in the next episode.